So we've been talking about integration, and I'm going to leave you with a problem while I'm gone, and I'm going to go ahead and set it up for you. So this is going to be a triple integral, and I'm going to go ahead and write it out the way it might look, as if this was set up in a textbook, or let's just call this a challenge problem. So I'm going to put the triple integral there, and then one of my variables is going to be r, and in this case the function is r squared. And I also have a variable that's going to be theta. And the function for this is going to be actually sine theta. Okay, and then I don't have a function for phi. I have a constant for phi. So I'm not going to represent anything there. It's just going to be the number 1 that's going to be implicit. So now if I put the differentials here, so these are the elements that I want to integrate over. I can say dr, d theta, and d phi. Okay, so we haven't talked in too much detail about spherical coordinates, but you probably recognize the r and the theta and the phi from the conversations that we did have. So what I'm going to do now is I'm going to go ahead and put the limits here. Shouldn't matter the order in which I choose for the integrals, for the integrands. So I'm going to choose for r, I'm going to specify r equals, let's say 0 to capital R, which would be the constant. So r, small r is the variable, capital R is going to be the constant. Now for theta, I'm going to say theta equals, let's say, I'm going to go from 0 to up here. I'm going to say theta equals, let's go ahead and say pi. And now I'm going to say phi is going to be from 0 to phi equals 2 pi. And I probably could have given us a little bit more room, but I think this is all making sense. So I'm going to pause for a second while you think about what the right approach to start integrating this is. And I understand that we haven't talked too much about triple integrals except what we did briefly in class just last week. So I'm going to take some liberties here, and let's see if I can do this. Let's go ahead and grab just this integrand portion that is referring to the variable r. So I conveniently put the variable right next to the integrand. So I've got this component here, and I'm going to just move this all down here. And now I'm going to grab this differential, the dr. And let's move, whoops, if I can. So all I did was I'm going to start rearranging this triple integral, and I'm going to start organizing, I guess, by like components. So what we had talked about before was having the integrand that refers to the ranges of a variable. So in this case, the variable is r. I have the function of r, which in this case is r squared, and the differential, which is dr. So far so good. I'm going to go ahead and put this up. I meant to select, I'm going to put this in a bracket, indicating that this is a quantity, and I'm going to multiply it by another quantity that I'm about to put in a bracket. You may have already guessed, I'm going to start grabbing the like components for theta as well as the like components for phi. And let's go ahead and do that now. So if I can just go ahead and grab the phi. Again, the order won't matter. So now I've got my phi component here, and here's my d phi. Gotta learn how to select this. There we go. So again, no function for d phi, or I should say the function is just a constant. It's just 1. So I'm going to do theta. So I'll grab the integrand. Bring that over here. And in this case, I do have a function. I have the function sine theta. And I guess I'll have to bring this out to fit it. And now I'll grab the d theta. So think about the difference in this form of this problem and what we had originally written down. So I'm foregoing a formal treatment of what I just did, but basically we organized all of the like variables and integrands and differentials, and we're simply multiplying them together. So I can treat this as three separate problems. So if I know the integration rules for this block in brackets, I'm going to get an answer that I will be able to multiply by the result of this integral and the result of that integral separately. And that's exactly what I'm asking you to do. So now the next question would be, are you able to do these integrals? So what is it that you know or don't know about integration that would allow you, to pull this off? So I'm going to give you a little bit of a tip. There's plenty of places to get this information. This is just one, but it's a nice, convenient, package. It gives a pretty good discussion of calculus in general. But what I really wanted to go to for this exercise was just to kind of home in on this, what we call integration rules. So we can just read it directly. Common functions, here's a number of common functions. This is the function inside the integrand with the differential, and this is the result of the integral. So these are indefinite integrals, which means you would expect to see the plus c, which is representing the constant. For us, we're doing a definite integral, which means we're not going to see the plus c because we're going to integrate and evaluate across the bounds. So my question to you would be, do you see those functions in this lookup table? So if I see here, I've got a function r squared dr, I want to integrate that. Well, if I go to the integration rules, sure enough, I see the square right here. So you should see the answer here, right? So you should be able to look up on this integration table and see that the integral of this x squared dx is x cubed over 3. So for us, we're just using an r variable. So that should be pretty straightforward. What about this one? Well, here's an integral of, it's just d theta. But we could also say, as we started the session, that there's a constant here. And we can't see the number 1 because everything can be multiplied by 1. So in this example, we can say that that common function fits this right here, the constant. So they're saying a is a constant here. In our example, it's just 1. So if we're integrating 1 times dx instead of a times dx, we would expect the answer to be x. So all you have to do is keep in mind that the variables are different. We're just using phi. So you should know what to do with that one. We have another one here that's sine theta d theta. So let's see if we can find that on the table. And here it is. So integral of sine x dx is negative cosine x. So you should have plenty of information in front of you to be able to do these integrals. And again, these are multiplications. These are not vector dot products. We've been talking about vectors. That's not what this is. This is just simple multiplication. So I'm going to leave it to you to work out that problem. And just remember to multiply all three together, and you're gonna be pretty interested in the result. And I want to challenge you with seeing if you can correlate the result that you get to any known quantity from geometry. So that's my hint as you go off and evaluate that problem, and we will talk about it after the break. So good luck.